Imagine a future where hydrogen fuel cells no longer rely on one of the rarest and most expensive metals on Earth. Imagine replacing platinum, worth more than gold, with something as common as iron or carbon, while still delivering clean power, zero emissions, and long-lasting performance. Imagine a fuel cell so affordable that hydrogen trucks, buses, trains, and backup power systems suddenly become economically viable everywhere, not just in well-funded demonstration projects. This is the vision capturing global attention as scientists announce promising advances in fuel cell catalysts that work without platinum. But is this truly a breakthrough or another moment where excitement runs ahead of reality? To understand where the science stands and what it really means for the future of clean transport, we must look deeper into what these platinum-free fuel cells actually are, how they work, and how far they are from commercialization. For decades, platinum has been at the center of hydrogen fuel cell technology. It is the engine behind the electrochemical reactions that allow fuel cells to convert hydrogen and oxygen into electricity and water. Without platinum, these reactions would be painfully slow, limiting power output to unusable levels. Yet platinum comes with steep drawbacks. It is expensive, geographically concentrated, difficult to mine sustainably, and subject to dramatic price swings that can derail entire supply chains. For fuel cell systems trying to compete against diesel engines or lithium-ion batteries, relying on such a precious metal keeps costs high and adoption low. This creates a paradox. Hydrogen fuel cells could transform clean mobility, but only if they can break free from platinum. Yet platinum has been essential for making them work in the first place. The push to find a substitute has been intense. Scientists across the world, from Europe to Japan to the United States, have spent years exploring alternatives. But replacing platinum is not simply a matter of swapping one metal for another. Platinum is uniquely good at the oxygen reduction reaction, the slowest and most demanding part of the fuel cell process. Most metals corrode, dissolve, or lose activity in the acidic environments of proton exchange membrane fuel cells. Many degrade quickly or form unstable structures under the stress of real-world operation. Thus, the search for a platinum-free solution has always been more like trying to reinvent the heart of the fuel cell rather than swapping out a component. That is what makes recent developments so intriguing. A new class of catalysts, especially iron-nitrogen-carbon (FeNC) materials, has demonstrated meaningful activity in the lab. These catalysts embed iron atoms within nitrogen-doped carbon structures, creating atomic sites capable of accelerating the oxygen reduction reaction. They do not mimic platinum perfectly, but their performance has improved enough to spark international interest. Early versions of FeNC catalysts suffered from rapid degradation, but newer designs show increasing stability thanks to improvements in carbon structure, atom anchoring, and radical-resistant frameworks. This progress is not limited to iron. Researchers are studying cobalt-based catalysts, nickel-based systems, manganese composites, atomically dispersed metal-free carbon catalysts, and alkaline fuel cell chemistries that give more leeway to non-platinum catalysts. Some approaches use graphene shells to stabilize catalytic sites. Others use porous nanocarbon frameworks that maintain high surface area and transport properties. Machine learning algorithms now help scientists design atomic positions with unprecedented precision. These advancements represent a convergence of chemistry, physics, and AI, all aimed at breaking one of hydrogen's biggest cost barriers. Yet it is essential to understand what breakthrough means in this context. Many shiny scientific headlines describe impressive initial activity, but longevity remains the true challenge. A promising platinum-free catalyst may perform exceptionally well for a few hours, or even a few hundred hours, in controlled laboratory conditions. But real hydrogen fuel cells in trucks must withstand thousands of hours of load cycling, humidity changes, temperature fluctuations, and voltage spikes. Heavy-duty vehicles especially impose harsh demands, and fuel cells must operate reliably for 30,000 hours or more to compete with diesel engines. Platinum-free catalysts rarely reach such lifetimes without degradation. This gap between lab results and commercial viability often gets lost in the public narrative. A breakthrough on paper does not immediately translate to a disruptor in the field. Even so, the progress is significant. Several FeNC catalysts have recently demonstrated stability improvements in acidic media, the most challenging environment for these materials. Some have shown reduced degradation rates thanks to enhanced carbon support structures or radical-resistant active site environments. A few newer designs operate better in alkaline fuel cell architectures, where corrosion is less aggressive, and platinum-free catalysts enjoy more favorable reaction environments. These advances push the field further than it has gone before. If platinum-free fuel cells ever reach commercialization, the implications will be transformative. The cost of fuel cell stacks could drop dramatically because platinum loadings represent a large portion of stack cost. Manufacturing could scale more predictably because the materials involved are abundant. Geopolitical risk would diminish since platinum supply is concentrated in a handful of countries. Hydrogen trucks, buses, forklifts, trains, and even marine vessels could become cheaper to build and maintain. The fuel cell economy would become more resilient, more efficient, and more aligned with global sustainability goals. The absence of platinum would also allow fuel cells to tap into markets previously considered out of reach. Small-scale consumer devices, off-grid microgeneration systems, portable power units, and low-cost residential fuel cells could become feasible. Hydrogen's role in aviation, especially for auxiliary power units, could expand if lower-cost, high-power density catalysts become available. Even hybrid hydrogen battery systems could evolve, combining long-duration hydrogen storage with rapid-response, low-cost fuel cell stacks. But we must also acknowledge the remaining barriers with clarity. Platinum-free catalysts still struggle with long-term durability in acidic PEM fuel cells. Iron-based catalysts generate radicals that can damage the carbon support, leading to mechanical and chemical breakdown. Many non-platinum catalysts lose activity faster when exposed to realistic humidity levels or hot start conditions. Fuel cell membranes and system designs optimized for platinum do not always pair well with alternative catalysts, requiring redesigns at the stack level. Scale-up processes for manufacturing these catalysts consistently and at high volume remain complicated. Stability, reproducibility, and impurity resistance are major industrial concerns. Even with these limitations, the momentum behind platinum-free research is accelerating. Some organizations are exploring hybrid catalyst layers that use minimal platinum, while relying on platinum-free catalysts to handle part of the reaction load. This could reduce platinum content by 80 to 90% while maintaining durability. Others are designing dual-phase catalysts where active platinum-free components are encapsulated in protective carbon shell structures. These intermediate approaches can ease the transition from platinum dominance to diversified catalytic chemistries. The story of platinum-free fuel cells is ultimately a story of scientific persistence. Breakthroughs in energy rarely occur overnight. Instead, they emerge from incremental progress, each discovery pushing the boundaries of what seems possible. 10 years ago, platinum-free catalysts showed almost no chance of relevance. Today, they demonstrate noticeable performance gains, meaningful scientific traction, and rising commercial interest. Tomorrow, they may provide a viable alternative pathway for fuel cell design. For industries betting on hydrogen, these advances represent hope. Hope that the cost structure of fuel cell stacks can improve, that supply chains can diversify, and that clean transportation can scale. For policymakers, the science provides justification to support hydrogen innovation and infrastructure. For fleet operators, the developments signal that fuel cell trucks may become more cost-competitive over time. And for researchers, platinum-free catalysts represent one of the most challenging and rewarding frontiers in materials science today. Hydrogen's future does not depend on a single discovery, but on a mosaic of innovations. From low-temperature fuel cells to graphene-stabilized catalysts to high-durability membrane materials. Platinum-free catalysts add another powerful piece to that mosaic. Whether they become the dominant fuel cell technology or simply one of several competing pathways, their progress matters because it pushes the entire hydrogen ecosystem forward. The question now is whether these catalysts can survive real-world testing, long-term degradation studies, and industrial-scale manufacturing. If they can, they may unlock one of the most important shifts in fuel cell history. And even if they cannot, The work will pave the way for better alloys, hybrid catalysts, and next-generation architectures. Hydrogen innovation is not linear. It is evolutionary, iterative, and continuously informed by discoveries like these. The idea of a platinum-free fuel cell working effectively is still in its early days. But the science is advancing faster than ever, and each new study edges hydrogen closer to a world where cost no longer stands in the way of clean power. If researchers continue to solve the durability and scalability challenges ahead, platinum-free fuel cells may one day move from laboratory curiosity to commercial reality. That transition, should it happen, would redefine the economics of hydrogen transportation and bring the world closer to a cleaner, more sustainable energy future.